Hello everyone, this is again Teacher Jenny guiding you on the 7th module for Quarter 3 of Mathematics 8 with the topic Applications of Triangle Congruence, taken from the module titled Applications of Triangle Congruence by Marlene D. Lucas, Rufo F. Duance, and Jocelyn Q. Gamad. At the end of this video, you are expected to apply triangle congruence to construct perpendicular lines and bisectors. But before we proceed to our lesson, let us have first this activity titled 4 Pics, 4 Words. Given here are 4 pictures. Can you identify 4 words which the pictures have in common? Good to hear that. Can you identify those 4 words? You're right. We have here triangles, congruent, bisectors, and angles. You might have enumerated several more words in mind, but let us focus on these 4 terms and look into their relationships and purposes to one another. Now let us see how we may apply or use these concepts in proving other statements. Let us begin with the isosceles triangle. Take note, there are 3 kinds of triangle according to the number of congruent sides. We have the scalene, the isosceles, and the equilateral triangle. For the scalene triangle, it has no sides equal. For the equilateral triangle, all sides are equal. And for the isosceles triangle, it has 2 congruent sides. We have here triangle MET. When we say isosceles triangles, take note, these are triangles with 2 congruent sides. So say for example, for this triangle, we have the 2 congruent sides, segment ME and segment MT. We call the angle between those 2 congruent sides the vertex angle. And the angles opposite those 2 congruent sides are called the base angles. Take note, in an isosceles triangle, the base angles are also congruent. So angle E is congruent to angle T. Next, we have what we call the isosceles triangle theorem, which states that if 2 sides of a triangle are congruent, then the angles opposite them are also congruent. So, in triangle ABC, if say for example, segment AB is congruent to segment BC, then the angles opposite those 2 segments are also congruent. The angle opposite to segment AB, that's angle C, and the angle opposite to segment BC, that's angle A, are congruent. In symbols, we have if segment AB is congruent to segment CB, then angle A is congruent to angle C. Next, we have the converse of the isosceles triangle theorem. If you can still remember, when we say converse, the hypothesis and the conclusion of a given if-then statement are interchanged. So for the converse of the isosceles triangle theorem, it states that if two angles of a triangle are congruent, then the sides opposite them are also congruent. So if, say for example, in triangle ABC, angle A is congruent to angle C, then the sides opposite those two angles are also congruent. So the side opposite to angle A, that's segment BC, and the side opposite to angle C, that's segment AB, are congruent. In symbols, we have if angle A is congruent to angle C, then segment AB is congruent to segment CB. Now let's prove the isosceles triangle theorem. Given here is triangle ABC with segment AB congruent to segment CB. Prove that angle A is congruent to angle C. Take note, segment BD is not on the given. That means this segment, since it's a broken line, it is just an auxiliary line. For the proof, we have the two-column proof. For the first column, we have the statements, and for the second column, we have the reasons. For our first statement, of course, it must come from the given. So we have segment AB is congruent to segment CB. Now for our second statement, draw BD as an angle bisector of angle B intersecting AC at point D. So we now have this line. The reason for that, every angle has exactly one bisector. Now since this line BD, is an angle bisector, then based from its definition, which is it divides an angle into two congruent parts, then we can now say that angle 1 is congruent to angle 2. Take note that we now have two triangles, triangle ABD and triangle CBD. So we have to prove that those two triangles are congruent to prove that angle A is congruent to angle C. So for our fourth statement, it is very evident that there is a common side between those two triangles, and that is segment BD. So our fourth statement is segment BD is congruent to segment BD, and that is by reflexive property. Now, since we had identified three congruent parts, then we can now say the triangle ABD is congruent to triangle CBD. Take note that there are two pairs of congruent sides and a pair of congruent angles. Now let us determine if the given pair of congruent angles is a pair of included angles or not. AB is here, BD is here, so the included angle is angle 1. CB is here, BD is here, so the included angle is angle 2. That means it's a pair of included angles. So we have the SAS congruence postulate. Now, since we had proven that those two triangles are congruent, then we can now say that angle A is congruent to angle C by CPCTC, or corresponding parts of congruent triangles are congruent. Let us now have examples on the application of the isosceles triangle theorem. First, find the measure of angle X. If you can still remember, the sum of the interior angles of a triangle is equal to 180 degrees. So if we're going to add the measure of angle X, the measure of angle Z and the measure of angle Y, that adds up to 180 degrees. Now take note that angle Z here is a right angle, therefore it measures 90 degrees. And based on the figure, segment XZ and segment ZY are congruent. So by the isosceles triangle theorem, the angles opposite those two sides are also congruent. So if angle Y measures 2x plus 5, then it follows that the measure of angle X is also equal to 2x plus 5. So by substitution, we now have 2x plus 5 plus 2x plus 5 plus 90 degrees is equal to 180 degrees. Combining like terms, we have 2x plus 2x, that's 4x, plus 5 plus 5, that is 10, plus 90 degrees is equal to 180 degrees. 10 plus 90, that gives us 100 degrees. Now, solving for the value of x, we have to isolate the term with the variable x on one side of the equation. That means we have to get rid of the constant, which is 100. So to do that, we can either subtract both sides of the equation by 100 or we transpose plus 100 to the right side of the equation. And that means we must change the operation. So from plus 100, it now becomes minus 100. Or for x plus 100 minus 100 is for x, and 180 minus 100, that is 80. Now we have for x is equal to 80. To solve for x, we have to divide both sides by 4. So for x divided by 4, that gives us x, and 80 divided by 4 is equal to 20. Therefore, the value of x is 20 degrees. Aside from this solution, we also have another solution. Now, since we have here a right triangle, and as what I have said a while back, the sum of the interior angles of a triangle is equal to 180 degrees. So since this is already 90, then that means the sum of these two acute angles is equal to 90 degrees. So for our alternate solution, we have the measure of angle x plus the measure of angle y is equal to 90 degrees. So by substitution, we now have 2x plus 5 plus 2x plus 5 is equal to 90 degrees. Combining like terms, we have 2x plus 2x, that's 4x, and 5 plus 5 is 10, is equal to 90 degrees. Now, transpose plus 10 from the left side to the right side. So we now have 4x is equal to 90 minus 10. And 90 minus 10 is 80. Now we have 4x equals 80. So to solve for x, we have to divide both sides by 4. So that is now equal to x equals 20 degrees. Now, since we are asked to find for the measure of angle x, that means we are looking for the value of 2x plus 5. So take note, the measure of angle x is equal to 2x plus 5. So by substitution, we now have 2 times 20 plus 5. And 2 times 20 is 40 plus 5, so we have 45. So the measure of angle x is 45 degrees. Let's have our second example. Given triangle JES, find JS, JE, and SE. Now, based on the figure, segment JS and segment ES have equal number of tick marks. That means those two segments or two sides are congruent. So for the solution, first we have to solve for x, and that is by using the congruent sides segment JS and segment ES. Segment ES measures 4x while segment JS measures 3x plus 2. So, to solve for x, we have to transpose 3x to the left side. So, it now becomes 4x minus 3x equals 2. Subtracting 4x minus 3x, we have x equals 2. Therefore, the value of x is 2. Now, since we have solved for the value of x, we can now find for the measures of the three sides of triangle JES. Let's start with the measures of segment JS and segment SE. Take note, those two segments are congruent. So since JS is equal to SE, then both sides equal to 3x plus 2, or you can use 4x. So by substitution, we have 3 times 2 plus 2, that is equal to 6 plus 2, so we have 8. So the measures of segments JS and SE is 8 units. Next, let's solve for the measure of segment JE. On the figure, JE measures 5x minus 1. So by substitution, we now have 5 times the value of x, which is 2, minus 1. 5 times 2 is 10, and 10 minus 1 is 9. Therefore, the measure of segment JE is 9 units. Now, let's proceed to the bisectors. Can you still remember what are bisectors? That's great. When we say bisectors, these are lines that divide an angle or a segment into two congruent parts. So we now have here what we call perpendicular bisector. This is a line which cuts a line segment into two equal parts and forms 90-degree angles. So given here a line segment, let's name it using its endpoints as segment TH, and another line which passes through segment TH, and we name it line M. If line M cuts segment TH into two congruent parts and forming a 90-degree angle or a right angle, then that means line M is a perpendicular bisector of segment TH. Let's now have the perpendicular bisector theorem, which states that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. In here, we have segment AB, and the perpendicular bisector is line CD. Now, since point C lies on the perpendicular bisector of segment AB, then that point C is equidistant from the endpoints of the segment. And the endpoints of the segment are point A and point B. That means if segment CD is the perpendicular bisector of segment AB, then segment AC is congruent to segment BC. So that's the perpendicular bisector theorem. Now let's prove the perpendicular bisector theorem. Given here is segment CP perpendicular to segment AB, and segment CP bisects segment AB. Prove that segment CA is congruent to segment CB. So for our proof, we have first, segment CP bisects segment AB. That is from the given. For our second statement, by the definition of a line bisector, since segment CP is a line bisector, then it divides segment AB into two equal parts. So we have segment AB is congruent to segment BP. Then we have the other given that segment CP is perpendicular to segment AB. Then for our fourth statement, since CP is perpendicular to AB, then that means angle CPB and angle CPA are both right angles. So we have angle CPA is congruent to angle CPB by the definition of perpendicularity. Then of course, since we have here two triangles, then they have a common side, and that is segment CP. So by reflexive property, we have segment CP is congruent to segment CP. Now, since we have stated three congruent parts, then we can now say that those two triangles, triangle CPA and triangle CPB, are congruent. That is based on the SAS congruence postulate. Since we have two pairs of congruent sides and a pair of congruent angles. And those angles are the included angles. So since those two triangles are congruent, then all their corresponding parts are also congruent, which includes segment CA and segment CB. That is by the CP-CTC, or corresponding parts of congruent triangles are congruent. Next, we have here angle MAT. Then we have a ray here. It's ray AH. If angle MAH is congruent, if angle MAH is congruent to angle HAT, then if angle HAT measures 50 degrees, then the measure of angle MAH is also 50 degrees. Now, based on this illustration, ray AH is a line that divides angle MAT into two equal parts. So, what do we call now ray AH? Very good. We call it an angle bisector. Now let's have the angle bisector theorem, which states that if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. So if segment BD bisects angle XBY, and point D lies on segment BD, which is the bisector, and DX is perpendicular to segment BX, and segment DY is perpendicular to segment BY, then angle DX is congruent to angle DY. That's the angle bisector theorem. Now we have the converse of the angle bisector theorem. If a point is equidistant from the sides of the angle, then the point lies on the bisector of an angle. So on this figure, Segment DX is perpendicular to segment BX and segment DY is perpendicular to segment BY. And segment DX is congruent to segment DY. Then, segment BD bisects angle XBY. So, that's all about the angle bisector theorem and its converse. Now let us apply what we have learned about bisectors. Let's have our first example. On the figure, segment LO is perpendicular to segment OV, and segment VE is perpendicular to segment EL. And segment OV is congruent to segment EV. If the measure of angle OLV is equal to x plus 14 and the measure of angle ELV is equal to 50 minus x, what is the measure of angle OLE? So take note, we are looking for the measure of this angle. It's angle OLE. And the given angle are the two angles which are parts of angle OLE. Now, from the given, since LO is perpendicular to OV and VE is perpendicular to EL and OV is congruent to EV, by the angle bisector theorem, we can say that segment LV is an angle bisector of angle OLE. That means segment LV divides angle OLE into two congruent parts, and those are angle OLV and angle ELV. Then that means that the measure of angle OLV is equal to the measure of angle ELV. So by substitution, we have x plus 14 is equal to 50 minus x. Combine like terms, so we have x plus x and 50 minus 14. So x plus x, that's 2x, and 50 minus 14 is 36. So what is now the value of x? Very good. X equals 18. Now, since we have solved for the value of x, then we can now find for the measures of angle OLV and angle ELV. So by substitution, we have x plus 14. So that is 18 plus 14 by substitution. So it is equal to 32 degrees. So measure of angle OLV is equal to 32 degrees. Now take note, angle OLV is congruent to angle ELV. So since the measure of angle OLV is equal to 32 degrees, then it follows that the measure of angle ELV is equal to 32 degrees. So to solve for the measure of angle OLE, we simply have to add the measures of those two congruent angles, angle OLV and angle ELV. So we have 32 degrees plus 32 degrees, that is 64 degrees. So the measure of angle OLE is 64 degrees. Let us have another example. On the figure, segment KT is the perpendicular bisector of segment EI. If segment KI is equal to 4x plus 15 and segment KE is equal to 7x, how long is segment KE? So first, using the given that segment KT is the perpendicular bisector of segment EI, let us identify the congruent segments. So from the definition of perpendicular bisector or a line bisector, name the two congruent segments. Very good. We have segment ES is congruent to segment IS because segment KT divides segment EI into two congruent parts. Now, by the perpendicular bisector theorem, what other pairs of congruent segments can you give? Very good. We have segment EK is congruent to segment IK and segment TE is congruent to segment TI. Now, since on the problem, we just want to look for the measure of segment KE and the given are segment KI and segment KE and the given and on the given and the given measurements are for segment KI and segment KE. So we will consider segment EK is congruent to segment IK. Equating their measurements, we have Ki is equal to Ke. By substitution, we have 4x plus 15 equals 7x. Combine like terms, so we have to transpose 4x to the right side. So we now have 15 is equal to 7x minus 4x. That gives us 3x. So what's the value of x? You're right, it's 5. So if x equals 5, how long is segment KE? Awesome! We have KE equals 7x. So by substitution, it's 7 times 5. Therefore, we have 35. So KE measures 35 units. Do you have questions? If you have, don't hesitate to type them on the comment section. But before we end this video, remember that isosceles triangles are triangles with two congruent sides. The isosceles triangle theorem states that if two sides of a triangle are congruent, then the angles opposite them are also congruent. So, for the converse of the isosceles triangle theorem, it states that if two angles of a triangle are congruent, then the sides opposite them are also congruent. When we say perpendicular bisector, it is a line which cuts a line segment into two equal parts and forms 90-degree angles. So when we say perpendicular bisector theorem, it states that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. And when we say angle bisector, it's a line that divides an angle into two congruent parts. So when we say angle bisector theorem, it states that if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. And lastly, the converse of the angle bisector theorem states that if a point is equidistant from the sides of the angle, then the point lies on the bisector of an angle. That's all. I hope you have learned a lot from this video. Thank you for watching.